Okay, guys, you guys popping too fast. All right, so hey, Polly confesses. Um, my Chinese typing is still in the kindergarten level. All right, so maybe I'll just say greet by saying it verbally. Good morning, Hong Ming and Ryan. Hey, Ryan. And sorry, Yong Yi. Yeah, sorry. Yes, it's still very challenging for me because even nowadays I still don't type Chinese all that much. Okay. Um, yeah, and good morning, Aslam. You're doing great, Aslam. And Matthew, good to see you. And Junhuan, Zhixiang, Tasha, Cheng En, Yanjia, Zhuxun, and Eniko. Good morning to you all. You know what? With what we've already talked about yesterday, so you know what the assignments to submit, okay, end of this week. So there's nothing more to say in the announcement, and we'll go ahead and dig into the topics. And before that, some of you might be a little bit anxious, waiting for the exam two results. Okay, again, hey, as long as you're doing your best already, whatever grades you receive, don't mind all that much. Okay, try to adjust yourself a little. All right, so today all we will be talking about are routing, internet routing, particularly the traditional type of routing. In fact, next week is still going to be about the traditional type of routing. Okay, so the first video will be we'll be playing. Hi, good morning, Cassandra. Cassandra, you've done much better this time. I'm very happy, and Guo Chen is also very happy to see your progress. All right. So first video. Okay, yeah, good to see you popping in, Ming Huang. So first video today is more an overview of chapter 5. Okay, so guys, take things easy. You can be relaxed watching this video. There's nothing important there. It's just to give you a bigger picture what's coming up, okay, this week and next week. Chapter 5, Network Layer, the Control Plane. Control plane is also what Polly likes to joke about, the better half of the data plane. Now, the reason for that is this. If you think about data plane, that forwarding function there, what it does is simply, right, for each incoming packet, do a table lookup, and you know what to do with the packet. Okay, so for each incoming packet, one table lookup, and that's it. There's nothing really intelligent about it, right? The only thing the forwarding is doing just table lookup, and it's just pattern matching, right? But hey, we are sending all sorts of packets coming from different sources, and they're going to different destinations, right? You cannot be sending these packets to arbitrary directions and hope that they will reach the destination. No. So that table there is really where the intelligence is. That is really, okay, guiding the packets to go to the right direction, eventually reaching the destination. So the data plane, the forwarding function, although very busy, working tirelessly trying to forward packets, okay, but it's actually simple, stupid. Intelligence is right here in the control plane. And the intelligence is implemented using these, the routing algorithms. Okay, so routing here, what I meant as a function is to find a path, okay, for a particular source to be able to send packets to a particular destination, or to find a path so that packets belonging to a flow can flow through the network, okay, with the right amount of resources reserved. Okay, so routing algorithm there, very intelligent. So in fact, the first part of chapter 5 is going to sound a little bit like you're attending an algorithm course. So Polly will be speaking about two general routing algorithms. Okay, so they are graph algorithms. So provided a graph, okay, if you think about it, a network having machines connected by cables is a graph, right? Points connected by lines. So provided a graph, we could calculate, we could compute the shortest path from one arbitrary point to another point. That is what the magic of the routing algorithms are. So these two general routing algorithms will be implemented on the internet as two routing protocols, OSPF and BGP. We'll talk about these routing protocols later after we finish describing the general algorithm. Now, these routing protocols are running on the traditional routers, where you have the data plane and the control plane. So the routing algorithm is running in the control plane. Okay? The control plane of each router might be communicating with the control plane of other routers. And together, they complete the task of calculating routes, and in turn generating the forwarding table, and in turn install the forwarding table to the data plane, and in turn the forwarding function, okay, can be working really fast. Now, the new model of doing routing is called SDN, software-defined networking. So the one that's doing the route computation is the controller. Okay, this is also known as the what? Remote controller, because in SDN, okay, the model is slightly different. You still have the data plane doing the forwarding, but the control plane is implemented outside of the routers. Okay, in fact, powerful machines somewhere remote. That's why these controllers are also called the remote controllers. Okay. And between the remote controllers, routing, okay, is being done where we generate the flow tables, and the CA, the control agent, now in the data plane, okay, that's taking in all these tables being transferred from the remote controller. Okay, in between, there's this open flow protocol. Okay, now you should know after chapter 4. So after the control agent receiving the flow table, the flow table gets installed, and therefore the SDN routers can do flow table lookup, okay, do generalized forwarding. Now, the remote controller here, okay, it's actually quite general. Inside the remote controller, you could implement multiple routing algorithms, such as the one used by traditional routing. You can also implement other routing algorithms, and in addition to all these routing algorithms that could be running simultaneously, and you pick and choose a particular route for a particular pair of source and destination. You could also actually specify preferences, or specify costs, okay, or specify other functions. Okay, so SDN's remote controller, being very general, okay, is actually working like pretty much a regular computer, okay, or expensive servers. So on these SDN remote controller, okay, we run operating systems, elaborated operating systems, such as ODL or ONOS. Okay, so these are two different operating system architectures, and both have big camps of supporters. So yeah, SDN routers are made available today that both operating systems can be installed, okay, to support route computation, flexible route generation, flexible flow table generation. Okay, so these protocols, as well as these two, okay, of the technical components in chapter 5 concern the routing function, the second important function in the network layer. In the control plane, okay, we also implement some protocols that is to do this, the management. Okay, so management of the routers, or the routes, or the packets traveling certain routes. Okay, so those are called the ICMP. So ICMP there is to allow generation of special messages from the routers or from the host to the routers, and routers generating something back. So these are there for the network admin to sort of probe the network to find out, okay, where and what might be going wrong inside the network. SNMP. Okay, so SNMP there, the management protocol is more there continuously tracking, okay, the statistics of the network. For example, number of packets traversing a router, number of packets traversing a route, okay, number of routes on a router, and things like that. So that the network admin can know better the status of the routers, the status of the routes. Okay, so again, for management purpose.
All right, so that was the overview of chapter 5. Okay, and now the video is short, only 2 minutes, but this is a very important review of what chapter 5 is doing, routing. And just like when we were talking about chapter 4, forwarding, there's traditional forwarding and modern forwarding. In routing, there's also the traditional routing and the modern routing. And later on, you'll find that the modern routing it's not like it runs a different routing algorithm. It's more that it's more general, just like the generalized forwarding. All right. So here's a quick review, an important review of routing.
Let's go real fast through 5.1, the introduction. Again, network layer, we run two major functions, forwarding and routing. Forwarding is about moving packets real fast from one router to another. Routing, however, is for each router to generate this forwarding table or flow table, or to determine the routes for the packets to move, okay, from one to another router. So in chapter 5, we focus on the control plane here. The two models, okay, for route computation are these, the traditional routing versus the SDN routing. In the traditional routing, each router implements part of these routing algorithms, and so the route computation is somewhat distributed, and the routers work collaboratively to come up with the best routes. Okay. So there's per router control plane doing the route computation. But in SDN, okay, the route computation is more centralized, running on powerful machines, and also somewhat distant from the physical routers. So centrally controlled. And this control is called the remote controller, as they are being physically distant from the router. More specifically, in traditional routing, okay, the routing algorithm is implemented and running on each of these routers, and they'll be interacting with each other to generate the best routes, therefore coming up with the forwarding tables. Okay, so in the data plane, yeah, there's this forwarding table in the data plane. The control plane there runs the routing algorithm, and together they generate the forwarding table and forward it and install it in the data plane. Now, the modern routing, the SDN routing, works this way. Okay? There's going to be a remote controller there, okay, doing all the computation and then interacting with the local control agent to install these forwarding tables, or more precisely, flow tables. So router, yeah, data plane here, having these control agent, and then at the control plane, we have powerful machines running the remote controller. Remote controller interacting with the CA, setting up these flow tables.
All right, so traditional, each router will do the route computation individually. Modern, with the SDN router, the mega controllers, the one or two controllers will compute the routes for the entire network. But they'll be using the OpenFlow to install these routes, okay, or these forwarding table, flow table, into individual routers. Okay, so you see the computation model quite different, the architecture different. Now, second topic today, this is the most important topic in chapter 5, just like RDT in chapter 3 in the transport layer. So routing. So first video is to say what routing algorithm is doing, and essentially try to find a route from one point to another in a network is a graph problem.
Now the core of chapter 5, the routing algorithms, or the routing protocols. So a good routing protocol there should be able to identify good paths or good routes from the sending host to the receiving host through this network of interconnected routers in the middle. So that is essentially trying to come up with a path. Okay? A path is a sequence of routers, one connected to another, and connecting the initial source to the final destination, okay, such that this path here is the least in cost, so we pay the least, or the delay is the shortest, or the promised bandwidth there is the highest, therefore the congestion level will be the lowest. Okay, so finding a good path, that is the goal of a good routing protocol or routing algorithm. It's also one of the top 10 problems in computer network, just like reliable data transfer, just like congestion control. In the next couple slides, Polly is going to introduce this new term called graph. A network, okay, of routers interconnected by links is a graph. So let's focus on the network in the middle here. What you see is that we have router U, router V, W, X, Y, Z. So we have a set of routers, okay, and there are 6 of them. Now between the routers, we have also links. So link UV here connects router U and router V. Similarly, UX here connects router U and router X. VX, V here, X here. Yeah, VX is the link connecting router V and router X. Link VW, connecting router V and router W. So you see, we can go over all the links defined here, and this forms the set of links interconnecting the routers. And coincidentally, a graph is also defined in a very, very similar way. A graph consists of the set of nodes and the set of edges interconnecting the nodes. So N here stands for nodes, and here E here stands for edge. So if you consider the routers being nodes, yeah, so the set of router here is the N here. If you consider links being the edges, then E here is the set of the edges. With the set of nodes, set of edges interconnecting the nodes, we do have a graph. So a network here is also a graph. And such an abstraction is really, really convenient later on when we're introducing the algorithm. It could also be useful when we're talking about other kinds of networks. So for example, in the application layer, chapter 2, For P2P, okay, you see there, okay, there are peers here, there, all around the internet. And we establish connections between the peers, right? So we could do what? P2P communication. So if you consider each of these peer as a node, and these TCP connections or UDP connections connecting the peers as an edge, there, you also have a graph. You also have a P2P network. And you can also run a routing algorithm, okay, on a P2P network, if you think about it. And now we can talk about this other thing, okay, it's called the link cost. So associated with each link, okay, on a graph like this, you see a number nearby, that is the link cost. To denote the cost of a link connecting router X to X prime, we use this notation, CX prime. So CWZ, connecting router W to router Z, the link here, yeah, the cost of that link is 5. Right? That cost, okay, can be set in a variety of ways. For example, set it as the inverse of the bandwidth available. You can also set it to the inverse of the traffic level. You could also set it simply to a constant, such as, 1. Every link costs the same, 1. Okay. So that is link cost. Now the cost of a pass, okay, is essentially also very simple. From the source x1 to the destination xp, it's the sum, okay, of all the link costs connecting from the source to each of the routers along the path, all the way till the destination. So it's the sum of the costs from the source to the first hub router, x2, c, x1, x2, plus c, the first router to the second router, x2, x3, and so on and so forth until the last router, xp minus 1, to the final destination. Okay. So let me use an example. Let's say traversing from U to Z, and we take this path. Yeah. The cost of the path will then be adding 2 to 3 to 5, and that will be 10 here. All right. So the goal of routing algorithm is essentially to find the least cost path, okay, between a pair of nodes, okay, from source to destination.
All right, so internet routing, a network is essentially a graph. Finding a route in a network is finding the shortest path in a graph. Good. Now, next video is also important, but also shorter. You will hear Polly compare and contrast the two algorithms, okay, that we really use on the internet. Okay.
And Polly will be introducing 2 routing algorithms next. First is called the link state algorithm, second, distance vector. The link state routing works this way. Inside the network, each router, okay, in the router, it implements an algorithm. Before this algorithm can be triggered, the router needs to wait to have the complete topology and link cost information. What I meant by complete topology is this. Each router will need to know N, the set of routers composing the network. E, the set of links interconnecting all these routers in the network. And link costs of all the links, okay, connecting the routers in the network. So each router needs to know how the network looks like globally before the routing algorithm can be triggered. Another characteristic is this. The link state routing algorithm will run in just one pass. So provided global information of the network, trigger routing, route computes, and completes. As a result, each router not only knows the best route to all possible destinations, it actually knows, okay, all the best routes from arbitrary source in the network to arbitrary destination in the network. So the router there, very informative, knows how the network is like entirely and knows all the paths, okay, for all the possible destinations and source pairs. On the contrary, in distance vector, routers no longer require global information. The routers also do not do one-pass route computation. Rather, the router only needs local information, namely, a router only needs to know how it's physically connected to the immediate neighboring routers and the link cost to the neighboring routers. And that's all. The route computation begins. With very minimum information, the computation gives you suboptimum results. Okay, so each router there, after running the distance vector algorithm, will know just slightly better than, nothing. And that information is definitely not quite good enough to give us the least cost path. So what distance vector routing does is there. Each router will then, after some initial computation, exchange the result of the computation to the neighboring routers. Neighboring routers would also exchange what they know slightly better to the router here. Now, this router in the middle, after receiving slightly better information from the neighboring routers, can recompute and see if even better paths have been discovered. So if the router again discover, better paths, then tell the good news to the neighbors. Similarly, neighbors would also tell slightly more information to the router. As such exchange expand, gradually traveling through the network. All the routers in the end learn about converge to the least cost path. So the process you see, computation, exchange, computation again, exchange again, computation yet again, exchange yet again. So the process is very iterative. It's going to take some time, but eventually, as the information propagates through the network, everyone converges to the least cost path. So a very different model of doing route computation. Link state routing being global, distance vector routing being local. Now, another way of classifying the routing algorithms is this, by judging at how the routes are being updated. Static routing is not updating the routes. So this is only for the network that is not changing frequently. And we know that this kind of network doesn't really exist these days. So all the routing algorithms that we're introducing are working this way, dynamic. That is also saying that routes can change, link costs can change. Routers could suddenly be dead and then or suddenly being boot up. So we'll try to update these routes, repeat the computation, periodically, or in case we detect there's a link cost change or no change, or some other changes.
All right, guys, time for pop poll. So I'm taking a poll now. Now, after that video, on the first impression, you see that there are two routing algorithms or two routing protocols. First is called link state, second called distance vector. Link state later on we'll just refer to it as LS, and the distance vector, dB. So on the first impression, you notice that LS is classified as global, dB is classified as local. So on such a first impression, which one do you prefer? LS or dB? Interesting. I'm very happy to see that you guys are now holding up to your own choice. Yeah, feel free to take your own pick. Yeah, Ryan, DV, it sounds cooler. Okay. That's a perfectly fine reason. Hey, very interesting, isn't it? Some say DV, some say LS. It does look that more of you like distance vector. Probably because there's a little bit more complexity. Interesting. And Ryan, thank you for providing your reason. Sounds cool, right? Many of you probably say, hey, I know Dijkstra algorithm. That sounds simple, And distance vector, I'm not quite sure exactly how it works, That seems cooler. You know what, distance vector, it is cool, very interesting, And we'll talk about that next week. But we might introduce the spirit, the idea of distance vector, and why having link state routing already, which is reliable, straightforward, why do we need another routing protocol? So guys, hold on, hold on. Let's talk about the straightforward one, the link state routing. So first is an introduction video. It would explain what it does.
Now finally, the link state routing algorithm. So what's implemented there essentially is the Dijkstra's shortest path algorithm. This is very well known in graph theory. Again, as mentioned, in order for this algorithm to work, we need the global information, network topology, link cost. And this information is acquired by sending these link state broadcast messages. So each router will be sending information about itself and how it connects to other neighboring routers and what is the link cost to the neighboring routers. And that information from each router needs to be broadcast around the entire network until every router on the network receives link state broadcast report from every other router. Okay, then all nodes will converge to the same information, same network topology link cost, and therefore beginning to compute the least cost path. So once the computation is done, we get the forwarding table to install to the data plane. Okay? Now, something extra is this. The computation itself is iterative, okay? But it's not working iterative like the distance vector. The distance vector's iteration is computation, exchange, and computation, exchange. The computation part and the exchange part is being iterative to each other. The iterative here meant, okay, there's a loop. Okay? The computation is actually working a loop, iterating through multiple loops. Therefore, okay, if we have k destinations, it takes 8 loops or 8 iterations to compute the route. Okay, so, yeah, the algorithm itself is looping within itself, but the computation will be done, okay, all at once without exchanging further information with the neighboring routers. Let me introduce these notations before I bring up the pseudocode for the Dijkstra algorithm. First is CAB. This is the cost of the link connecting router A and B. You should know already. Yeah. What's a little bit surprising to you is this. The cost CAB could be infinite, okay, because there's no direct link connecting the two routers, and therefore the cost is infinite. Second notation is this, DD. Okay, small d here is indicating that for a particular destination, the path from this router doing the computation to this destination, what is the cost of the path currently? Okay. So capital D here actually stands for distance. This is also saying what is the current distance to a particular destination D for this router doing the computation. Now PD here, D again is the destination, okay, and PD is to indicate for this router to reach the destination D, okay, along all the routers on the path. What is the previous router before reaching D? Okay, so predecessor node along the path until reaching D. And prime is the set of nodes whose least cost is already known.
All right, so that was to prepare you for the next video. And this video coming up is very important. All right, guys. This video, I think almost about 6 minutes. All right, almost about 6 minutes. And it's going to come in 2 parts. And the whole thing is essentially the Dijkstra algorithm, but adapted to work with a network, a real network. So there are going to be 2 phases. The first phase is just to initialize things, okay, and then the second phase you see that there's a loop, okay, and we need to iterate through pretty much all the nodes in the network. So here's the video. Right after the video, no worry, we'll also walk through an example, a complete example, and then a quiz allowing you to exercise working through the algorithm in the lecture, okay, during the lecture time. So 6 minutes.
So here's the pseudocode of the Dijkstra algorithm. There are 2 phases, the initialization phase and the looping phase. A looping phase looks really complicated, so let's not worry about that part yet and focus on the easier part, the initialization phase. So what we're doing first is to initialize the n prime, the set of nodes we know already the best route to. And we're quickly including A. The reason is this. Whenever we execute once the Dijkstra algorithm, we give also the source of the path. So A here is the source of the path we're trying to discover. In fact, after running through a Dijkstra algorithm, we will discover, okay, the shortest path to every other node in the network. Okay. Now the source, in case A is also its destination, hey, it's trivial, isn't it? We just don't send it down. Send it to 127.0.0.1, the IP address for the local host. So we can initialize n prime to just the source node safely. Second thing we do is actually a for loop here. Okay, inside the for loop, we'll go through all the nodes, okay, in the network other than the source. So all other nodes, okay, and for each node, okay, B, we check whether it's directly connected to the source. If it does, we've discovered a way to go to this particular destination, isn't it? And the distance to it is the link cost between node A and node B. Now, if the node is not adjacent to A, then it's going to trigger this line here. No route has been discovered yet to this destination B. Therefore, distance to the destination infinite. Okay. Now, from the description, you probably also see in order to find all pair shortest path, you need to repeat the Dijkstra algorithm, providing a different source address. Okay. Now the exciting part, the looping phase. It looks a bit complicated, but if you focus first here, okay, the loop is going to go until all the nodes are in the M prime set. That is also saying that the loop is going to go until all the shortest paths have been discovered. Okay, the shortest paths to all the nodes have been discovered. And you probably guess that, hey, one of the things that will be changing in the loop is the M prime set. Okay. Yeah, indeed. Okay, the first part in the loop is exactly to do that. We are gradually adding nodes into the M prime set. Okay? And the node we pick to add is this. Okay? The node such that the distance to it is currently the minimum. Because adding this I to M prime set is also saying that the best route to I is already discovered. Okay? So why is the minimum di here is suggesting that the best route? This is also the shortest distance to I. Now, think. Originally, okay, we have A in the M prime set. Okay, the D, B there existing with significant values are these. The nodes directly connected to the source. And therefore, the distance to each of these nodes, okay, is the link cost. Now, in the loop, okay, the first two lines here is going to include what? The node with the smallest link cost to the source into the M prime set. Is that making sense? Okay, is the shortest distance, okay, to that particular node exactly that? Is there a way to discover another path to that node that is going to be lower than the link cost between A and I? Not possible, right? Because all the other links cost is higher. If there exists another path to I, the cost is definitely going to be longer than this because all the other link costs are higher already. Okay? So di here is indeed the minimum, and I here we've already discovered the shortest path. So it's safe to include it into M prime, in fact. Now, having added I to the M prime set, this is also saying that we already discovered the shortest path to I, and the shortest distance is di. So I know there is something really nice to exploit. Okay? Through I, we can potentially discover shorter paths to other nodes. Okay? We have not yet discovered the shortest path. Okay? So what we're doing here next is to go over for all j nodes that are directly connected to I. So for all the neighbors of I, and not yet in M prime. So all the neighbors of I that we have not yet discovered the shortest path, then we update dj. Okay, and that is what this formula is saying. Okay. So the new dj is the minimum of the two, the existing dj and okay, the distance to go from j directly to I and di. So the shortest distance from I to the source. So di plus Cij. So this is what the comment is saying. The new cost to j is either the all cost to j or the shortest path to I plus the link cost from I to j. So what we're doing there is to update dj. Okay, if there is a shorter path, that's just added in. If there's a shorter path, that's override the bad path. Okay, things like that. So you see, what we're doing in the looping phase is actually not much different from what we're doing in the initialization phase. So this part of the looping actually corresponds to this part of the initialization, isn't it? Okay, including nodes that we know for sure. Okay, what is the shortest path? And then here actually corresponds to this. Okay, try to discover the shortest path possible. Okay, by updating based on the information that is known.
All right, so that might sound a little bit fuzzy, but you get a rough idea. Okay, so let's walk through an example that will make things clear. Okay, so this is the first part of the example. There's going to be the second part that is to iterate through the whole loop.
So that was the walkthrough of the pseudocode. I know it might appear a bit fuzzy to you. Let's go over a concrete example. So in the example, again, we have 6 routers and their links. Each link comes with a cost. And let's assume U is the source and Dijkstra is going to do the computation starting from U. initialization phase says let's include the source into the n prime. Therefore, we see u here appearing in n prime. Next thing is to go over all other nodes. Okay. So x, w, v, y, z. Those who are adjacent to u, then we set the minimum distance to it, set the predecessor to reach it. Otherwise, if they are not directly adjacent to u, set the distance to infinite. So for y and z, we'll see, okay, this should be infinite. And for vwx, v, the distance to v should be what? The link cost between the source and v. So between u, v, link cost 7. So 7 should appear here. The predecessor for such a path definitely going to be a, because we just added a to the n prime set, right? And we're reaching v through a direct link. Therefore, the previous node must be the source, u. For w, link cost being 3, so 3 here, predecessor again u. For x, link cost being 5 and predecessor u. And yeah, 7u, 3u, 5u, infinite, infinite. Okay, so we just finished initialization phase of the Dijkstra algorithm on the example. Now, entering the looping phase. First thing we do in the looping phase is what? To find the I that is not yet in n prime such that the shortest distance to I is the minimum, and we add that I to n prime. Alright, so let's go over the di. Okay. 7, 3, 5, infinite, infinite. Which one is the minimum? Yeah, 3 here is the minimum. Therefore, I is w this time, and we'll include I into the n prime set. That is why. Next, we see u and w both in the n prime set. And then we can now do the second thing we do in the loop. We'll update the minimum cost. And we're going to do this for all the nodes adjacent to, what is the I being added there? W, right? So we'll go over all the nodes adjacent to W. Okay, and that is now already in n prime. So who are the nodes adjacent to W? X, Y, V, oh wait, oh yeah, Y disconnected, okay, because there's one link here, and U, all right. But you know what? U is already in the n prime set, so let's remove this. So there's just 3 nodes, okay, can potentially be J, and we need to update the minimum distance and the predecessor node. So what we'll be doing here is to exploit W here, okay, as a hopping node. So V here, okay, there's another path, right? Originally we had this direct link, but now there's an alternative path through W, which is what? 3 plus 3. Okay, the minimum distance to W plus the link cost between V and W. And that is how much? 6. Is 6 better than the existing minimum distance to W? Existing minimum distance to W, existing minimum distance to V is 7, and that is indeed better. Okay, so 6. And in case it's better, the new path is better, we'll set the predecessor to the new node we're hopping through. So V is now taking W as the predecessor, and the cost, minimum cost from the source, is only 6. Second neighbor, Y. Previously, dy infinite. Currently, if we use W as a hopping node, 3 plus the link cost between W, Y, 8. Together, 11. Obviously better than infinite. And the predecessor is what? W. Third neighbor of W, X. Exploiting W as the platform, hopping, and then adding the link cost between X and W, that is 7. Is 7 better than dx? Dx was 5. 7, oh, yeah, in X's case, not better, so we'll keep 5 here. Z not being connected, it will remain the same, so remaining infinite. And therefore, we should see 6W here, 5U here, 11W here, and infinite here.
All right, so that's the first part of the example. Okay, now let's iterate through the whole loop and include all the nodes into n prime.
So what do we do next? Well, we're in the loop, and we are not in the condition to end the loop yet, so we're not yet done. We have only U and W in n prime. Okay, there are more nodes, okay, we could consider adding to the n prime set. And the way we add to the n prime set is to pick I such that di is the minimum. So dv6, dx5, dy11, dz infinity, which one is the minimum? Yeah, x is the one we're picking this time. So we'll include x into the n prime set. And we see there, x here is the I. So we'll be examining all the nodes adjacent to x next. So x is here. The adjacent nodes include u, w, y, and z. But you see, yeah, we'll be going over all the nodes adjacent to y, but not yet in n prime. U and w are already in n prime, so we will not be updating du, not updating dw. So let's update dy. The way to do it is to follow the formula. What is dy now? The current cost, 11. What is the newly discovered path cost? What is the new path? Well, one can actually go to x and then using x as a hopping platform to reach y. And the total cost is 5 plus 7. That is 12. This time, the new path is actually not better than the existing path. So we keep 11w here. The other neighbor, z. Okay, what is the current cost? Infinite. So infinite here. Cost to x is 5. And the link cost from x to z, 9. So the new path discovered is 14. And the predecessor is x, which is better than infinite. So 14, x here. Now, v is not even a neighbor of x, so we'll just not update vv and pv at all. So, and that's why we see 6w here, 11w here, and 14x here. So this is the second iteration in the loop. And next, pick I again with the minimum di. 6, 11, 14. Therefore, we include this time v into the n prime set. Right? So 6 here included, v included to the n prime set. And therefore, the I is v. So I here. We'll go over all the adjacent nodes of v, which includes u, w, and y. And that's now already in n prime, so that includes u and w. The only node that we need to actually update the d for is y. So we'll be updating dy. Existing dy, 11, right here. So if v here is the hopping platform, the cost to go to v, the cost to go to v is actually what? 6, okay, through w. The link cost from v to y is what? 4. So 6 plus 4, 10. Is 10 better than 11? Yes, it is, so let's update it. And this time the predecessor is what? V. Okay, so that is also saying this path here was no longer good, and this is actually a shorter path. Now z is not directly adjacent to v, so we just leave this entry down. That is why we see 10v and 11x. Good, so yet another loop. We pick another I with the minimum di. 10, 14, therefore we pick y next. And y is included into the n prime set. So y is our I this time. So y here. Go through all the adjacent nodes that are not already in n prime. So x already in n prime, w already in n prime, v already in n prime. The only one that is not in n prime is z. So let's try to update the distance to z. And again, follow the formula. Existing distance to z is 14, so 14 here. Using y as a hopping platform, which says, the minimum distance is 10, and the predecessor is v, so it's this path here. And we are adding the link cost from y to z, which is 2. 10 plus 2, 12. Oh wow, so this new path here is better than the existing path, though. Let's update this to 12, and the predecessor is what? Y this time. And so we should see 12 and y here. And the last loop is to include the only remaining node, that is y, actually, that is z here, okay, into the n prime set. And there are no neighbors adjacent to z that's not yet in n prime. So this part we don't have to execute for the last iteration. Okay. And by now we've completed the Dijkstra's shortest path algorithm, okay, for an example of 6 nodes.
All right, so that's a full example. So this is a pop poll number 2 today. So I'm asking, is this the first time you hear about the Dijkstra algorithm? Yes or no? Oh, okay. So you guys have all have heard about the Dijkstra algorithm, I guess. Oh, no, not quite. For Yuting, it's the first time. Yeah, I guess for many of you, it's something known already. Okay, good. Oh, okay. So for some students, okay, this is the first time. Okay, good. This is just for Polly to know whether we can go faster maybe next year or not. Okay, I guess even if this is your first time hearing about it, it's somewhat intuitive. It's not that hard. Okay, not exactly tricky like many other complex algorithms. Now, we walk through a whole example. The question remaining is this: hey, after the Dijkstra computation, what we find is this table, right? 0 iteration, first iteration, all the way, including until we include all the nodes into the n prime. But what should the forwarding table look like? Okay, so this last video, 1.5 minutes, tells from this table we have derived using the Dijkstra algorithm, how we turn that into the forwarding table.
Just a couple more notes to construct the shortest path to a particular destination from the source. Say from U to Z. Okay, what it needs to do is just to track the predecessor node, okay, and let's trace it all the way back to the source. So Z is the destination. That's traced back from the predecessor of Z, which is indicated here being Y. And who's the predecessor of Y? Yeah, it's stated here, which is V. Who's the predecessor of V? Stated here, W. Who's the predecessor of W? U. That is the source. Yeah, therefore, you see, this is the shortest path from U to Z. The shortest path to X, yeah, indicated by the predecessor, which is U itself. And so we could actually reconstruct the shortest path by just tracing back the predecessors. And you see also here, if we trace back, okay, for all possible destinations to the source, you see also a tree rooted from the source U, okay, to all the destinations. And this is indicating also the shortest path to all the destinations. And such a tree is also called the shortest path tree. And Dijkstra algorithm there is also used to calculate, okay, to generate such a shortest path tree. Second note, the D values, okay, when we're picking the I, can have a tie. So in that case, we just have to break the tie and picking one of those.
All right, so what you're seeing essentially is that for destination X, the next outgoing interface is essentially the one going upwards. For all the other destination, the one that goes sideways. Okay, that's how you construct the forwarding table. All right, and it's time to exercise. So this is quiz 40. So I have here another network. Okay, so let me go here. So we have a different network. Okay, so what you're asked to do first is to fill step 0, so this row, essentially following the Dijkstra algorithm, especially the initialization part of the algorithm. And then, okay, complete step 1. Okay, so the second row, which is to do the first iteration of the loop. Okay, now let's go to the Discord channel, W13 quiz 40. Okay, guys, I will not be taking the fast responder. This is the time for you to exercise the Dijkstra algorithm and fill this table. So you guys will have 8 minutes time, okay, to think this through and write it out. Feel free to just download the picture and write down the picture and upload it, okay, if that is easier. If you want to avoid making sure that what you're typing will align perfectly. Okay, so 8 minutes, that's start counting time. good. I see that you guys got this. Okay, a couple teams missed out on the py of of step one, the second row. So I've already left a comment. So guys, check your solution out, or cross check other team's solution. Then you will see. Yeah, right. Okay, good. And guys, you know what? We've completed learning the link state routing. All we need to talk about are the issues, what's not so good about link state routing. Okay, but we'll talk about those after taking a break. It's now 11:18. Let's resume the lecture 11:28. Okay, break time. Okay, let's resume the lecture. Okay, good. I see that you guys all got the Dijkstra algorithm, aka the link state algorithm. Okay, let's talk about the issues in link state routing. First, let's talk about the computation complexity.
Now with the two examples walked through, you see the Dijkstra's algorithm, although look a bit cryptic at the beginning, it's in fact quite straightforward. Initialization phase, 2 steps. Looping phase, 2 steps. Looping phase is the one that we take multiple iterations, we spend more time with. So that is going to bound the complexity of the Dijkstra algorithm. And within the looping phase in each iteration, which of the steps is taking the most time? Yeah, the second step. Inside the second step, we're actually checking all nodes j. Okay, that is adjacent to the node we just added into n prime. Okay. And inside each iteration in the inner for loop, what we do is this, the min operation. And this is in fact to compare the value of the current shortest path to the newly discovered path, right? So d to I plus the link cost between ij. So it's a comparison between this value and this value. So you have the looping phase, and inside there's an inner loop that is doing a lot of these value comparisons. Now, if we consider a fully connected worst case for Dijkstra algorithm, inside the network there are n nodes. Okay. In the first iteration, so only the source is in the n prime. How many j's is connected to the source? Yeah, it's fully connected. Therefore, n-1 nodes, they will all be j, and we'll need to do min for each of these j. First iteration, we'll need to do n-1 comparison. Second iteration, how many? Because there's one more node being picked, being included into n prime. So number of j in the second iteration, only n-2. Third iteration, and we can go on until the second last iteration, we have only one node remaining connecting to the new node being added to the n prime. In the last iteration, the second step is not going to be called because there's no j remaining. So if we add all these together, this is the number of comparisons. N multiplying n-1 divided by 2. And this is in the scale of n squared, big O n squared. So big O here is actually to say that the Dijkstra algorithm in the worst case runs in the scale of n squared. That means the time complexity, the growing trend of Dijkstra algorithm is this. When n approach where the network goes really big, the time requirement goes in this trend, like an n squared curve. Now, if it's only big O n, the curve is linear, a straight line. Sorry, the line is not very straight here. Now, there's an implementation available for Dijkstra algorithm such that we could do away with only n log n. Now, this is better than n squared. So again, n is here, n squared growing really fast here, and n log n is actually kind of in between. Faster than the pseudocode we've investigated, and better than a linear algorithm. So, nice to have an efficient implementation, even though the original Dijkstra algorithm is not so good.
All right, so complexity essentially big O n squared, but because there's an optimization for the Dijkstra algorithm, so one can achieve n log n. Now the second issue is very interesting. It's called oscillation. And you probably see from the video what's in the rest of the slides. Okay, when we set the link cost to traffic load and allow the value of the traffic load being adjusted dynamically, really depending on the current traffic load, then you might have this route oscillation problem. So this video is a little bit long, but it is to show, the oscillation. So you will see the best routes go one way, suddenly switch to another, but then the next cycle switching back, and it will never end.
There's one very special issue with link state routing that's called the path oscillation problem. And it happens when we set the link cost dynamically based on the amount of traffic going on the link at the time. Now let me explain using an example. So we have 4 nodes in the example, A, B, C, and D. A is the traffic sink. All traffic goes to A. B, C, D are traffic sources. A generates one portion of the traffic and send it over past BA. E generates E portion of the traffic. E here is a very small amount, much smaller than 1. And C is taking the CBA path to send traffic to A. D generates also one portion of the traffic and it's taking path DA to send to destination A. And at this point, we need to update the link cost based on the traffic going on the link. So for link DA, amount of traffic is one portion. For link BA, amount of traffic is what? One portion plus the E portion from C. So total cost, 1 plus E. The cost for link CB, amount of E traffic from C only. You see also here, okay, this direction, BC, there's no traffic, therefore link cost is 0. Similarly for AB, similarly for AD, and similarly here for both direction in link CD. So we finish updating the link cost. After a while, link state routing is going to trigger Dijkstra algorithm running again, right? As I described, link state routing is a dynamic routing algorithm. We do periodic update, and sometimes we use also network events to trigger recomputation of the routes. Link state routing there does periodic recomputation. Okay? It's going to recompute the routes based on the link cost now. So let's see. B here, we'll see two possible paths to go to A, right? One is to go counterclockwise to A, the other clockwise to A. So this direction here, the cost is what? 1 plus E, because there's only one link and the link cost is 1 plus E. If we take this other path, B, C, D, A, yeah, the path cost is the sum of the link costs, 0 plus 0 plus 1. Okay, so if we take the clockwise path, okay, to go from B to A, cost is only 1. And this is 1 plus E, therefore B is going to choose to go this way to send traffic to A. C, also see two possible paths. Okay, if we take this direction, cost is E plus 1 plus E, and that is 1 plus 2E. The other direction, cost is 0 plus 1, therefore 1. And therefore, C would choose to go also clockwise to send traffic to A. Similarly, D sees also two paths. Okay, this direction here, cost is 1. This direction, 0 plus E plus 2 plus E, 1 plus E. So altogether, 1 plus 2E. So still, okay, this direction better. So D is also going to take the clockwise path, okay, the same path to A. So after the route computation complete, you see B, C, D all change to send traffic clockwise. And then we need to update the link cost again, right? So given the previous cost, we come up with the new routes, and we will then, okay, update the link cost, and we come to the new cost again. What is the new cost now? Okay, on link BC, yeah, there's only one portion of the traffic. On link CD, yeah, 1 plus E. On link DA, 2 plus E. And that is why we see 1 plus E, 2 plus E, and all the rest of the links, 0. Once we update the link cost, after the next period that the Dijkstra algorithm is triggered, we compute new routes. So B will then try to see the cost to go this direction and the cost to go the other direction. The cost going counterclockwise is now 0. Cost going clockwise is now 1 plus 1 plus E plus 2 plus E. That's 4 plus 2E. So dominantly, BA is the better path. C's cost going this direction, 0 plus 0, cost is 0. The cost of the other direction, 1 plus E, 2 plus E, 3 plus 2E. So C is going to switch going this direction to send the traffic. What about D? Going this direction, 0 plus 0 plus 0. Going this direction, 2 plus E. So D is going to switch for the first time to go counterclockwise. And that's why in the next moment, you see traffic begin to change direction completely. Okay? From all clockwise, okay, one period before to counterclockwise the next period. So given these new costs, we calculate the new routes all going counterclockwise, and we update the new costs again based on the traffic. DC is now 1. CB is now 1 plus E. And BA now 2 plus E. And that is what you see here. 1 plus E, and 2 plus E. As a result, B sees this pass costs 0. This pass costs 2 plus E. B switch the other direction. C sees this pass, really high, 3 plus 2E. And this other direction, 0. D, this direction, 0. This direction, super bad, 4 plus 2E. So all of them would switch back like this. And the link cost gets updated again. 1 on this link, 1 plus E on this link, and 2 plus E on this link, which is identical to 2 periods before. Okay? And you see the next period is going to be like, yeah, the previous period. And the traffic is going to oscillate infinitely, right? Clockwise, counterclockwise, clockwise, counterclockwise. So that is the path oscillation problem if we set link cost dynamically in link state routing. Okay, that's running the very straightforward Dijkstra algorithm. Just be careful here.
Okay, so oscillation. That actually looks interesting, right? And the packets will still arrive at the destination, by the way, even with the oscillation. It's just that it will probably see very frequently the packets arrive out of order. Right? That is not something that people like, okay? Especially when you're sending traffic over UDP. TCP, however, on the other hand, will try to make sure that the packets will arrive in order before passing them up to the application layer. And this is this oscillation issue is also why the link costs, okay, on the internet are very often set to some fixed value. All right. Next video is also to talk about an issue. Okay. Now let's recall a little bit Dijkstra algorithm. Before we can run the algorithm, we need to see the graph. Okay. That is also saying, as a router in a network that runs the link state routing, we need to know the graph of the network. And how is that done? That is actually done by the link state report we mentioned very early in the intro video of link state routing.
To put simply, link state routing works this way. Each router implements the routing algorithm. It's going to wait until the total information of the network is in place. Then it calls the Dijkstra algorithm. At the end of the calculation, we get the least cost path from this router to every destination possible in the world. So that is essentially the shortest path tree. Now that router, being the root of the shortest path tree, we'll see there are multiple branches out to the rest of the world. Taking one branch, it gives you the shortest path to a certain set of destinations, another branch to another set of destinations, yet another branch to yet another set of destinations. And so, from the tree structure, okay, we can construct the forwarding table, and that is how the forwarding table is calculated in the control plane. Next is just to install it into the data plane. Now, the only part I'm going really quick without mentioning much is this: how we get the total network information so we could apply the Dijkstra algorithm in the first place. That is done through this link state broadcast. Each node, okay, in the network is going to generate link state report based on very local information. That includes the ID of the node itself, the ID of the immediate neighbors, and the cost, okay, on the link to these immediate neighbors. Okay, so these are the local information. Node, the neighboring nodes, and the link cost to the neighboring nodes. So all these local information is going to be in the link state report coming from the node. This link state report is going to be broadcasted, meaning, okay, going out through the entire network, being received by all other nodes. So all nodes eventually will receive link state reports from every other node. Okay. And these link state reports from every other nodes, including the node's local information, is going to be used to restore, okay, the total network. Let me give you an example to illustrate how that is done. We have a very simple network here, only 4 nodes. Okay, you see U connects to V, U connects to W, U connects to X. Okay? So if we are node U, okay, and generating node U's link state report, it's going to contain this, the ID of the node itself. Yeah, there are three neighboring nodes, V, W, X, and the cost on the link to these nodes, 5, 3, 7. So U to V, link cost 5. U to W, link cost 3. U to X, link cost 7. Similarly, V is going to generate its link state report, which is going to contain only one entry. It connects to U, link cost 5. The link state report from W should look like this. Two neighbors, U and X, cost being 3 and 2. Link state report from X is contained two entries, U and W, link cost 7 and 2. So each of these nodes, U, V, W, X, is going to broadcast their link state report. And every node in the network is going to receive its own local information and every other node's link state report. Therefore, node U here is going to receive the link state reports from V, W, and X, which we know already look like this. The way to restore the network topology is this. Okay. Node U knows the local information. It connects to V. It connects to W. It connects to X. Cost is 5, 3, 7. Now, seeing node V's link state report knows that V and U is connected. Cost is 5. V, U, I'm U, so I know. Okay, and the cost is 5. W's report is going to tell, okay, the cost to U is 3, which you already know. Oh, W is also connected to X with link cost 2. So W connect to X link cost 2. X report says I connect to U, so X connect to U, you already know. X reports also that it's connecting to W link cost 2, which you already have. And you now manage to reconstruct the total network information from receiving link state reports from all the nodes in the network. And it's contributing also so that other nodes receiving U's link state reports can also reconstruct the total network. So you see this one here, U connecting to VWX. Yeah, isomorphic, okay, of the network there.
All right, so that's how you construct the graph of the network using the link state report broadcasts. But you see, broadcast that information over the entire network. That is a lot of control traffic, and each router to store such a graph that is order of n square. Okay, so traffic load and memory requirement for individual router is actually high in link state routing, and that is the last issue.
So that was the last piece of the puzzle, link state routing. Other problems you see here. Now you know a little bit about the link state broadcast. Yeah, some of you might see this. These link state broadcasts, it's going to travel the entire network. And it's coming from every router, right? So you have n copies of these packets going to n nodes. The bandwidth consumption is again at this scale. And to store the topology information in the router, right? So we discussed the complexity of Dijkstra algorithm. We only talk about the time complexity. We have not yet talked about the space complexity. It's also huge, right? In the worst case, you have n nodes fully connected to every other node. Then you have what? N square number of links. You need to store costs, okay, for all these links. Ugh. Not very scalable when the network goes big, when n goes large.
All right. Can you imagine the entire internet runs on link state routing? It's very hard to imagine that, right? Every node needs to store the graph of the entire internet. Wow, that's going to take a lot of memory space. So the network engineers realize that using just link state routing is not going to work or scale well. That's why we have this second routing algorithm called distance vector. So this video, very brief, it is just to give you an idea of the distance vector being running more like a rumor network, okay, a network that people passes rumors around.
So you see, link state routing works fairly well for small networks where n is small. For access network, institutional network, local area network, it might be okay. But for the entire internet's backbone, there's no way we use link state routing. And that takes us to the second routing algorithm, distance vector in the chapter. So distance vector routing is exactly here to address the space complexity, to address the message exchange complexity in link state routing. If you think about it, the reason that the link state routing takes so much space, requires sending of so many messages, is because in order for the extra algorithm to run, we need the total network information. So the question to ask is this: can we come up with a path? Can we discover best paths, best routes without knowing the global information? You know what? It's possible. We just need to be a bit patient though. Okay? So Polly here might have two neighbors, Alice and Bob. Bob and Alice do not know each other. Okay? There's no path existing from Bob to Alice. But if Polly shares how Polly knows Alice to Bob, then Bob will know that there's one way, right, to reach Alice, which is through Polly. So I tell my neighbors, and you tell yours, okay, about what you know. Gradually, okay, the network, okay, will spread the good news out and discovering a path, a route, okay, to every other node in the network. That is the general idea of distance vector.
All right, so general idea. Decision based on local information, meaning neighbors' information, okay, or information provided by the local neighbors. Second, as soon as your neighbors discover better information, you also can make better decisions. But in order to reach the optimum decision, it's going to take time because the neighbors will need to learn from their neighbors, and their neighbors need to learn from their neighbors. Okay. All right. So next coming up is to make sure you get the idea, to demonstrate the point that you, unfortunately, in distance vector, you make decision only based on neighbor information, local information. So 41 to 40. It should be 41 to 43. Okay, it's gonna be making decision based on local information. So let's go to the quiz 41. Okay, so guys, I need you to role play router X here in the network. So you are this guy, okay, X, and you want to send data to W. Oh, this is your destination. Okay, you do have two neighbors, Y and Z. Okay. And of course, you have the local information, so you know the link between U and Y is 9, and you need you know the link cost between U and Z is 4. Okay, and then now, neighbor Y tells you, you know what? Hey X, I know a way to W. But neighbor Z says, nah, no idea. Okay, I have no idea. You being router X, would you pass the data to Y or Z and why? Okay, let's go to Discord, channel W13, quiz 41. Oh, okay, I already see two teams. Hey guys, you have only 1 minute. Okay, the choice seems to be obvious. Let's see. Team 1 says definitely Y. Yeah, because Z obviously doesn't know anything about the destination. So you have only one option really to be realistic, right? Why? Because between Y and Z, Y is the only one at least knowing a way. Very good. Let's see. Yeah, Y, yeah, and Z doesn't, right? So chances higher you reach W better through Y, right? Now you see that this is almost like the rumor network, isn't it? Hey, you ask a friend saying that, do you know this other guy here? Yeah, he's on news, right? And the guy might know the person, and then the guy knowing the person better might clarify, okay, there's some mistakes in the news report, things like that. So this is very much like the human network and how human pass information. Yeah, obvious, okay, obvious, very good. Now, guys, come back. Quiz 42. Okay, you are still router X. Oops. You are still router X. Okay, you still want to send data to W. The network remains the same. But now, neighbor Y tells you, okay, I know a way to W, and I know the cost from me, from Y to W, is 3. And then your neighbor Z now tells you, okay, I also know a way, but you know what? It's going to take longer to get data to W through me. It's 10. Would you pass the data to Y or Z next, and why? Okay, let's again go to Discord, channel W13, quiz 42. Very good, you guys have found your way. Okay, team 1 says, why? Because the sum, the total cost, right, from U to W is lower. 9 plus 3 is 12. And XZW will be 4 plus 10, which is 14. Okay, let's see. Team 13 is making decision based on the cost. And guys, you guys are great routers. You know the goal is to find the shortest path for a router. So routing is essentially a graph problem, finding the shortest path. Very good. You guys are routers functioning perfectly right. Very good. Why? All right. Good, let's come back. So up to this point, you see, routing will still work, right? As long as you know a neighbor who knows a way to the destination, you just pass it over. And they will also try to pass it, best effort trying to pass the data. And eventually you will reach the destination, okay? And the more information you get from your neighbors, right, the paths gradually get better. And eventually it will converge. All right, now let's try another quiz. Okay, this is number 43. You're still router X, okay, and you still want to send data to W. Okay, now. What if, okay, we play God and we know exactly what the subnet is, okay, and therefore we see, hey, there's a link between Y and Z. Previously, we don't know. But now we suddenly see that there's a link between Y and Z. And the cost is 2, right? The information your neighbor Y and Z tell you remain the same. Okay, now this time, as router X, which one would you pass the data over and why? Okay, let's see what you guys say. So channel W13, quiz 43. Okay, yeah, it seems, right? Because if you pass to Z, okay, so Yongyi explained a little bit better, right? You could do XZ and hope that Z sends it to Y, and Y knows a way to W, which is only 3, right? So in a way, Z to W, okay, maybe the next moment in time, Z will realize the total cost is 5 instead of what Z's been telling you, 10. So if that's the case, XZYW will be even shorter. That is 4 plus 2 plus 3, 9 only. Yeah. So let's see. Send to Y first. Okay, to Z and tell them to send, okay, send to Z and tell Z to send to Y. All right, so this is to ensure Z will do the right thing. Good. Yeah, so good, Eneko, well explained. You want it to go to Y, but this time you can send it through Z. So you find the local shortest path to Y. Actually, no, exactly not the local shortest path. Yeah, but essentially what I'm trying to say here is that if you do have global information, very oftentimes you see the route selected by distance vector is not the optimum. Okay. Yeah. Z and then Y and then W. Exactly. Hopefully the total cost is only 9. Very good. Okay, you guys are all very good as a router. Okay, so let's come back here. Yeah, so this is exactly the point that Polly want to point out. Okay, good. So distance vector a lot of times don't give the optimum path, and it usually takes time to reach the optimum routes. All right, good. So now we can move to the next video. Okay, so this video here finally explains the spirit of distance vector routing. Okay, there's a question from Aslam. Does X know the route between Y and Z? Okay, Aslam. Allow me to explain. So maybe I can come back here just a little bit. Okay, let's spend a little bit more time here. If X, Y, and Z are distance vector routers strictly, X only knows this, this, and this. X does not know this. Okay, so to answer your question quickly, X doesn't know too. Okay, I'm just saying that in quiz 43, if the router X can play God and see that, hey, the link cost between Y and Z is 2, there's obviously an even better route. And to make a point that in distance vector routing, if the neighbors are telling you suboptimum information, then the routes you come up with would also be suboptimal. Exactly. In actual internet routing, X would know. Okay. All right. So let's keep things simple, August. Okay. All right. So hey, let's go on. So this video here tells the spirit of distance vector.
That should give you a rough sense how a router discovers a route without seeing the entire network topology. That is asking the neighbors to help. So neighbors will be reporting how they know about the destination. Now you know the neighbor's cost to the destination, and you know the cost for you to reach each of your neighbor. So that be X and the cost from the neighbor to destination Y. You can calculate the sum of X and Y. If the value here is not infinity, you've discovered a route to the destination. But in order to discover the route that is the best to the destination, then you will need to check through all neighbors. Okay, for each neighbor, you find the cost to each of these neighbors. And you find out from that particular neighbor the cost to the destination. And you sum up, okay, X and Y for that particular neighbor. So you pick I such that Xi plus Yi is the lowest. There, you discover the best route, the shortest path. And I there is the next hub that leads to the shortest path to the destination.
All right, good. And the last quiz today, okay, so this is quiz 44. It's called the perspective and perception. Okay, so obviously you see in this picture, right, the object in the middle, simple, an elephant. But you see, this is because we can see the whole picture. Okay, even the smartest people in the world, when they are blindfolded, okay, what all they can do is just to feel the things, okay, nearby. So you see here, we have 6 scientists. They are all blindfolded in the picture, right? So the one sitting on top of the elephant feels the ear, and it's thin and flat. So the scientist says it's a fan, right? And the scientist on the letter touches the trunk, the body, the belly of the elephant. And it's like a big wide wall. So the scientist says, hey, it's a wall. Okay. This is how far you can reach. Okay. okay? And therefore, this is how much you know, all right? But these scientists, right, when they are shouting out, hey, this is a fan, and this is a wall, okay? But guys, over here, I'm here. This feels like a rope, okay? As more information are communicated from one to another, then you see a little bit better. You can infer a little bit better, okay? So now, quiz 44 is really asking this. Let me ask you to guess, okay? I have a secret item in the box, okay, question mark, okay? And I get a number of testers to come trying this item out. And so the first tester says, you know what, guys, it's a drink, obviously, okay? To me, it's a drink, okay? And then the second tester says, guys, it's cold. And then 3 more testers, okay, try the drink out. First one says sweet, second one says soft. And the last little girl says, hey, guys, it's chewy. Okay, now let's go to the score space. Channel W13, quiz 44. Okay, guys, what do you think it is? Okay, you have 2 minutes. Okay, team 1 says boba, okay. Anything from Starbucks? Okay. Can anyone come up with another cold drink that is sweet, soft, and chewy? I'm gonna give bonus, okay, to that answer. Okay, guys, feel free to update your solution, okay? Anything that's not boba. Okay, but guys, I need to say that, hey, you guys are right. I guess it's a little bit obvious, right? If I'm asking this in Taiwan. It is, okay, the final answer is boba. But I've seen previously, okay, from the class. Let's see. Team 10 says cognac. Okay, yeah, it's also chewy, right? Cognac. I think it's a Japanese chewy food. Jelly, exactly. Summer berry lemonade Starbucks refresher. Okay. Okay, I'm actually not quite sure if the Starbucks in Taiwan carry this product. Summerberry. I wonder what that is. Okay. Grass jelly. Grass jelly. Okay, so guys, grass jelly is another type of Taiwanese sweets that are being added to the cold beverages. Okay, or icy plates. Okay. Literally what I just ordered in Toronto. Cool. Can you send us a picture of that? Okay. Summerberry. Honey lemon juice with aloe jelly. Okay. Nice. Matcha with mochi. Oh, obviously, right? Mochi is chewy. But this is very Japanese. But hey, we're in Asia. Whatever drink with boba or jelly, okay. Boba tea with milk cap. Yeah, so it's boba. It's not exactly boba tea, but boba tea with extra milk cap. Okay, so it's like latte boba tea. Okay, boba added in soda. Oh, interesting. Oh, okay. I suddenly feel hungry now. Okay. Team 11, strawberry milk with mochi. Oh, this is from Coco, really? That looks really appealing. Oh, wow. I hope that it drinks as well as the picture says. Oh, no. I don't know. Is the expired milk sweet? No, it has a foul taste, right? Okay. It does taste chewy, I have to say. It's not exactly sweet. And coming out of the refrigerator, it's cold. Maybe if you added lots of sugar to it, then it will feel like it's sweet and chewy. Ooh, ouch. Coconut jelly, okay. If anyone is from Southeast Asia, yeah, this is a very frequent item. Oh, thank you, August. Summer berry. Very interesting. Yeah, lemonade is a perfect drink for summer. Okay. All right, guys. Hey, sorry for making you guys hungry, but we do have an important point to make here. Okay, distance factor is this. Okay, you don't need to store the information of the entire graph, which is huge, right? Does require memory space, and you don't need to pass the link state reports all around the network either. Okay, all you need to do is just talk to your neighbors. Okay, as they learn more, you learn more. So initially you get suboptimal routes, but it will still work. But gradually, when the information gets better and better, the network will gradually converge to the optimal route. Okay, or something close to optimal route. So maybe you didn't get the boba tea, but you get something like coconut jelly tea, the grass jelly tea, the spoiled milk. Okay, something close. All right. So that is distance vector routing. Next week, starting Tuesday, we'll introduce the formal algorithm of distance vector. It's based on this equation called the Bellman-4 equation. Okay. With that said, okay, I look forward to seeing you next week, and I say goodbye. Go get lunch. Okay. Yanjia, it's a safe answer. And by the way, for the series from 41 to 44, I will accept all answers. Okay? Okay. All right. Bye, guys. See you next week. All right. Bye. Looks really nice. Interesting. I guess you need to eat this with a spoon in addition to the straw, right? Mm-hmm. Honey lemon juice with aloe. Mm. Jelly juice. Mm-hmm. Oh, okay. Team 4. Banana milk. Pink chili. Oh, taro. Drooling. Drooling. Anything from stuff.